I'm going to ask my colleague, Chuck Stahlberger, to begin sharing his screen. So tonight's presentation is one that some of you might have even seen me give this before, but it's about electrification of the built environment. Now, it is something that we're having conversations about nearly on all of our projects, I'm sure everyone on this group, and the different ways of doing it. We wanted to share some best practices, what we've found of the opportunities with the different technologies, some lessons learned along the way, and how the electrification technologies fit into how we think about resiliency, not only in terms of energy sources, but withstanding climate change. So your speakers tonight are myself, your now former co-chair. For those of you that don't know me, I'm Patrick Murphy. I am the Director of Sustainable Design with Vanderwaal Engineers, and I'll let Chuck introduce himself.
Thank you, Patrick. Yep, Chuck Stahlberger. Work with Patrick over here at Vanderwaal in the building performance group, doing a variety of our energy modeling, sustainability consulting, and whatever else we need done towards towards furthering the sustainability of our projects. So appreciate the time, the opportunity to be here tonight, and looking forward to the discussion. So I think with that, Patrick, should we kick it off?
Let's get into it.
All right.
And we're going to move quick to try and get you all to dinner at 7:30 if you're not already eating with your camera off. So copyright presentation, it's AIA 2030, or it's AIA continuing education credit. Beth put in the chat the link. I'll try to remember to put it in there a couple more times, but look in the chat for the link to get your continuing education credit through the BSA. And so our agenda tonight, we're going to talk about the drivers of electrification, which I think a lot of us know, but we kind of put it in some context that might be new for you. Talk about what is electrification, what do we define as electrification, and those components and strategies to electrify buildings. We'll go through a couple of case studies that all look at the electrification angle from a different perspective, and then land on how you decide on your project what the right approach to electrify will be. So let's take it away, Chuck.
All right. So as Patrick said, I'm guessing a lot of the folks on the call here know, a great deal about this subject, are familiar with some of the trends that are driving us towards an electrified future here. Electrification at its core is really an effort to decarbonize. We're trying to reduce Scope 1 emissions, any emissions that are happening due to combustion in the building. We're trying to reduce Scope 2 emissions, which are coming from purchased electricity, purchased heating and cooling from some sort of district system, purchased steam. We of course also want to reduce Scope 3 emissions, which are due to things like business travel, employee commuting, fleet vehicles, et cetera, et cetera. But really, as architects and engineers, we are really focused on Scope 1 and Scope 2 and in reducing the amount of carbon associated with those uses through the use of cleaner sources of energy. And really that's what electrification is at its core. Make everything in the building use electricity and then use clean electricity to power those systems. So we can feel pretty good that this is going to happen, that energy will be clean because, at last count, I think 28 states had passed these renewable portfolio standards, or RPSs, which are pieces of legislation at the state level which required the utilities in those states to purchase greater amounts of clean energy over time. We have New England examples here, due to the local crowd here. We could see that pretty much we're going from about 20%-ish renewable in 2020 to 50% or more renewable in 2040, 2050, and potentially even more than that. So all of which is to say, the grid is going to be significantly cleaner, in 2040, in 2050 than it is now. And whatever we can electrify to leverage that cleaner grid is going to result in fewer emissions. And a lot of clients ask us, what is that, where's that electricity going to come from? And, I think many of us are aware, one source, of course, is going to be wind energy. Per the DOE's latest count, as of Q2 2021, wrapping up here, we have almost 120 gigawatts online in the US, roughly 25 million homes worth. And solar isn't far behind, 75-ish gigawatts in Q2 2021, another 15 or 20 million homes. And that doesn't count the, basically additional total amount, call it another 100% of that, which is in the pipeline for between now and 2030. So quite a bit of energy coming online, wind power, which can work at night, solar energy, which can work during the day, and all of which will be offsetting, fossil fuels, coal plants, even gas plants now going offline to be replaced by those sources of energy. So with that, I'm going to pass it back over to Patrick to talk a little bit about the theory behind electrification in the building.
Thanks. So we look at the choice of fuel of energy through a couple of different lenses. And so this will be one way of kind of comparing them on an even playing field and looking at them now and into the future. If you go to the next slide. So like Chuck and shared with you all, when we think about emissions, we as building design professionals are primarily going to be focused on scope 1 and scope 2. It is our responsibility to help our clients outright eliminate the use of fossil fuel from their facilities and in our designs, or to significantly reduce our dependence on them. And it's also on a number of architects and engineers in this area who work on central plants with some of our, say, university clients, or work at the utility scale as well to help leverage that ever cleaner grid, or work with clients on master plans towards carbon neutrality. The main philosophy behind electrifying is when you're using, especially in your larger facilities, when you're using hot water, or you can use hot water as your heating medium, we're talking about lower temperature hot water. You can produce water for heating that's up to 140 degrees relatively easily using readily available heat pump technologies that are all electric and can use that clean electricity grid. Whereas the heating mediums, say in more existing buildings and older buildings, were relying on hotter temperature water, 180 degree, or even steam, which you really do need fossil fuels to produce that, at least in any reasonable way. And so when we talk about electrification, we're also talking about shifting towards a lower temperature hot water, and that lower temperature hot water is agnostic to all the different technologies that we'll talk about in a moment. Now, in order to produce 1 BTU of heating, we are going to compare head-to-head gas condensing boilers, which up until relatively recently, and still frankly on a lot of projects, are still the baseline that we default assume, for a lot of owners assume. We're going to compare those to heat pumps. I'm using heat pump in a very general way. We'll get into the more specifics of different types in a moment, but the idea of a heat pump being this electrified refrigerant cycle that really amplifies the heat from a heat sink. We're also going to compare electric resistance. So the electrification movement of the pre-energy crisis that leverage electric resistance is not what we are talking about. And when you hear people talking about an electric boiler, we're going to tell you why that's not necessarily the best idea right now. In terms of efficiency, comparing them head to head, for every unit of energy you put in, you get a little bit less than 1 unit of energy out from a condensing boiler or electric resistance. But a heat pump can amplify that through the refrigeration cycle, through the heat sink, can get you 300, sometimes even more, percent efficiency to produce that 1 unit of energy in. You get 3 or more out. Now, in terms of emissions, and this is looking at 2025 projected emissions in Massachusetts. To produce that BTU of energy, the heat pump is already going to emit fewer emissions than the gas condensing boiler. And that's with today's electricity grid. But electric resistance actually emits a lot more emissions to produce that 1 BTU of energy. Now, the reason is the electricity grid is not necessarily cleaner than burning fossil fuel for, say, a condensing boiler right now. But when you combine the grid in its current state, which does have a number of renewables on it, and you combine that with the efficiency of the heat pumps, that's where you outpace condensing boilers. Now, those are the emissions in 2025, but as Chuck mentioned, the trend is to move towards a clean energy future, whether you do that yourself on your projects or as part of a portfolio, as part of the state. Electrifying gets you to zero emissions, potentially, if you can offset it with renewable energy. Whereas if you install that boiler, it's going to continue to emit for the life of the boiler. Now, frankly, and I don't want to be Pollyanna about this, we also need to consider the energy costs. And given that we all know electricity is more expensive currently than gas for the same unit of energy, to run that heat pump right now in Massachusetts with just state average energy rates, it could be a little bit more expensive to run that heat pump to produce that unit of energy than that gas condensing boiler. But again, you see that dramatic difference between electric resistance and the heat pump. So electric resistance is showing how much more expensive electricity is currently than gas. And the heat pumps are much lower and more competitive with the condensing boiler because of that efficiency. But this is the price today. We expect, there are a number of studies out, that the cost of gas will likely increase as buildings and owners shift away from gas. Fewer and fewer customers will be responsible for paying the costs of maintaining the natural gas infrastructure, and the cost of gas will go up. Whereas the cost of electricity, frankly, I'm not going to speculate. There's a lot going on in the electricity grid, so we'll see. Next. So Chuck's going to take you through a couple of the way we look at the different components and strategies, and what we mean when we talk about heat pumps.
Yeah, so like Patrick said, we talked about heat pumps there kind of theoretically, and not all heat pumps are created equal. The type you would use on a smaller, maybe multifamily project is not going to be the same that you're going to use on a larger, academic project, classroom, etc. And there are different applications for them in terms of what you would use for an HVAC system, for domestic hot water, how to electrify other loads. And we want to take a minute and just look at those technologies in a little more detail, so you can, maybe have them in the back of your mind on your next project that wants to electrify. So for heat pumps, let's start with HVAC. The first type, and this might be the one that we're most familiar with, would be an air-to-air heat pump. And that is exactly what it sounds like. We are pulling heat from one area, the outside, we are pumping it into another area, the inside, and heating that air. So we're pulling heat out of one source of air, we're rejecting it to another source of air, air-to-air heat pump. And these are very, very similar to what you might have in your home. You have an outdoor unit and an indoor unit, and you are running refrigerant between those to exchange the heat. These are, relatively low cost, compared to some of the other technologies that we'll look at. They do not take up a ton of space. You do have to think about refrigerant piping applications. They're modestly efficient, so they're not going to be, kind of a LEED platinum level of efficiency, but they're a good way for a project to get into electrification, kind of without breaking the bank. And from a capacity standpoint, these are really best served, best used in kind of compartmentalized zoned applications. Again, like a multifamily project, maybe hospitality, smaller types of projects. For larger products that need more capacity, we can go to an air to water heat pump, and that is pulling heat again out of the air. And I should take a second to address the concerns about heat pumps in cold climates. So up until very recently, heat pumps did not operate, frankly, super well below about 17 degrees Fahrenheit, and sometimes even higher. Even just in the last few years, manufacturers have made huge strides in their technology. They're doing things like increasing the surface area of their heat exchangers, baffling the units, making all sorts of little tweaks to their units to make them operate at much lower temperatures and to provide more capacity at those lower temperatures. So these units now can operate in our New England climate, even on the coldest winter nights, you know, providing pretty much 80 or 90% of the capacity that would provide anyway. So I want to get that out of the way and you know, make sure that I mention that, because that wasn't always the case. Heat pumps didn't always make sense in New England, and they do now. But anyway, so an air to water heat pump is going to pull heat out of the air. Again, even that cold air in wintertime, there's heat there that we can use. It's going to reject it to a water loop in the building. So that's going to allow us to serve a much larger area and to provide that, you know, modest to good level of efficiency to that larger area. If we go to an even you know, larger project or a, you know, even more energy or maybe load intensive project, something like life science, you know, or something else that has higher loads, we can go to a water heat pump. And so now we're pulling heat out of one water loop, projecting it to another one. And these are great because these can be, you know, intertwined with things like a ground loop to do ground source heating and cooling. We can do heat recovery using something like a heat recovery chiller or heat shift chiller. And there are a lot of, you know, going to a water loop opens up a lot of flexibility with you know, where we want to move heat around and efficiency associated with that. And, you know, no electrification presentation would be complete without talking about VRF, variable refrigerant flow. This is a system that's kind of taken the industry by storm, I'd say, in the last few years. Basically, it's a version of the air-to-air or an air-to-water heat pump on steroids. It allows the, you know, rather than using water to run heat around the building, we're using refrigerant. And so you get a lot of indoor units and one outdoor unit, and you get lots of heating and cooling sharing from those units. So you can have one zone in heating and another in cooling, and the heat is taken out of the zone needed cooling and is rejected to the zone needed heating. So rather than generating energy with our outdoor unit, we're just sharing it and getting a lot of efficiencies that way. Now, VRF can be a very efficient system for the reason I just said, but it also has a lot of what I'll call kind of non-energy considerations we need to think about. There's a lot of refrigerant running through the building with a VRF system. You know, the refrigerant line lengths can only be so long. So if we have a high-rise building, we have to think about how we're going to get the refrigerant from the outdoor unit on the roof down to the indoor units on the lower floors. So,
right. And the refrigerants that we use are both a safety potential issue, and they are, well, depending on the refrigerant you use, they can contribute more to global warming than a pound of CO2, sometimes dramatically more, a pound of refrigerant than a pound of CO2.
Right, so all of which is to say, VRF can be a very efficient system. It can be a very flexible system, but there's a lot that we have to think about other than just energy use when we're using VRF. So if this is something you're considering on your next project, definitely talk to your engineer and hash out some of these topics ahead of time, because they also affect things like space planning and, you know, riser sizes pretty significantly, because you're moving equipment inside and outside. So that was HVAC. In the interest of time, we're going to keep going here. Domestic hot water also can be electrified, and generally that's going to be with a heat pump water heater. These are, you know, like Patrick was saying, not an electric resistance water heater. This is basically that air to water heat pump, but instead of heating a hydronic HVAC loop in the building, we're going to heat a tank of water. These have lower recovery rates than a similarly sized gas heater. So if, you know, say you have a hospitality project right now that has a duplex condensing gas fired water heater, you're probably going to need 4 or 5 of these to make that same recovery amount as that you know, dual tank gas water heater. So they're not quite there yet in terms of the technology for higher load, you know, scenarios like a hospitality project, a multifamily project, anything else that needs a lot of hot water in a short amount of time. These are a great option for projects that maybe are only using hot water for hand washing, a couple other loads, and those smaller load projects. And these can be another source of heat recovery, because these actually pull the heat out of the ambient air around. So if you can locate this in, you know, near a kitchen, if you can locate it near maybe a locker room or fitness area, you're going to pull heat out of that area and actually use that heat to heat the water, rather than just rejecting the heat to the outdoors and then using some other fuel to generate heat somewhere else. So all of which is to say, great option for smaller heat loads. And you know, talking to manufacturers, they've heard our cry for larger versions of these units, and we're told that they're coming in the coming years. And lastly, a technology that is, you know, a little bit less mature than the others that we've talked about, but is certainly worth looking into, especially for those higher load projects, is wastewater heat recovery. And this is exactly what it sounds like. Wastewater, whether it's leaving the building or whether it's in a main passing near to the building, has a year-round temperature generally between 50 and 70 degrees Fahrenheit. It's kind of like a ground source where we're going to pull heat out of that year-round source and we're going to use it in the building. Now, of course, we don't want to have any odor concerns or other similar types of concerns. So there's a lot of infrastructure that goes into tapping into a sewer line and isolating that from the building. So there is a higher first cost associated with this technology. But because there's that nice even temperature available year-round, the energy savings associated with this are also very, very high. So this is a very good technology for those higher load projects that happen to be situated, with a lot of sewer resource, and certainly something we encourage you to look at on those higher load projects. Other loads, EV charging. I'm sure with the folks, with the group that we're speaking to here that we're working in the city of Boston. We know the city has pretty significant EV requirements where you have to have 25% of spaces on day one having chargers, the other 75% having future EV capability. Generally, those are level 2 EV chargers, think 30 or 40 amps of space. That adds up pretty quickly. So something you want to identify at the beginning of a project before you send a load letter to your utility. Laundry on projects can be a source of electrification. So rather than just using an electric dryer, which of course is electric, but is kind of the bad electric that Patrick talked about, electric resistance, consider ventless heat pump dryers. Not only is the dryer itself going to be more efficient, but the makeup air that you would typically need for a dryer and the dryer exhaust all goes away. So there could be some cost savings there too. And cooking is another way that projects can electrify. And not as much right now for a commercial kitchen. Food prep folks like their gas units. The gas cooker capacities tend to be higher than what's available right now with induction units. But for break areas, for kitchenettes, other areas like that, you can swap in an induction cooktop, and generally you'll get the same transient performance on that cooktop, and you'll do it without emitting any gas into the space. And a method that's been successful for us in our projects is to identify maybe one break area, one kitchenette, and kind of do a pilot. So that'll be the pilot induction area that lets the owner see how they like it, and if they like it, they tend to expand it from there. And if they don't, then gas cooktops can continue to work for the foreseeable future. So with that, I'm going to pass it back over to Patrick to talk about renewables and then to go over a few case studies.
Thanks. So I'm sure this group is very familiar with applying renewables to our projects directly to reduce the demand our buildings have on the grid, especially during the peak in the middle of the day. And there are lots of strategies with rooftop, with parking, even with awnings or cladding penthouses, with PV, like some of these projects. Then looking bigger picture, frankly, to get to net zero, especially to get there more quickly than the grid is going to help you get to net zero. Think about working with your clients about offsite renewables. So this is an example, a project I worked on at Lehigh University where, frankly, this lab building had a pretty high load, as lab buildings do, even though it was a very efficient lab. And it was in a relatively historic part of the campus. And so we needed to offset that energy offsite. And so we worked with the university to, as they were developing a large PV array on an adjacent site, worked with them on the contracting around retaining the renewable energy credits, which is important if you're going to claim net zero, for example. And so the interesting thing, that this owner had was that they had relatively valuable renewable energy credits in Pennsylvania, and they did sell those, and they purchased offsetting RECs. And so some of that delta in price helped fund this infrastructure that directly impacted their local grid. So One thing I have been fortunate enough to learn is I've worked with, and a number of you are part of the Building Green Sustainable Design Leaders group, the perspectives from different parts of the country. So this is, you've probably heard of the duck curve in California. This is what Texas calls the armadillo curve. And this is showing the solar energy that's produced during the day, but it tails off rapidly at night. So think about, as people are getting home and starting to cook, or starting, turning on their heat when they get home, or charging their cars, there's a surge in demand right when solar is falling off. And so one of the ways to help mitigate this and align the time of use with the time of production of that renewable energy is energy storage. So what energy storage does is take some of the energy that's produced at that peak, if you go to the next slide, Chuck, and then stores it for use relatively quickly, in that surge in demand in the early evenings. This is really impactful in places like California, and also potentially in Texas as well. Next. So we'll quickly go through some case studies, showing you the different dynamics and how we've thought about applying electrification principles to different types of projects, in different locations, different project types. So this first one is one I'm excited about at Cape Cod Community College. It will be a net zero teaching lab. And here it was driven to electrification by that net zero goal, but also interestingly, this project kind of straddled the Massachusetts code update, and it was more advantageous to go electric and take advantage of the efficiencies of those heat pumps to comply with Mass LEED Plus, things like that, the 20% threshold above energy code, or better than energy code. So we used air source heat pumps on the roof. So basically an air-cooled chiller, but that can also produce heating. And we optimized the floor plate and the roof ratio so that we would have a really optimal roof area for PV. Now, we looked at going purely all electric, just cutting the cord from gas altogether. And what we found, this was when we were earlier in design, the technologies that Chuck talked about with those air source heat pumps, they did come with some issues that we didn't want to incorporate into our project. We wanted to kind of have a broad, multi-state project, multiple manufacturers going after this project to keep the bidding fair. And so we had to back up the air source heat pump when it did get really cold with another form of heat. We looked at electric resistance boilers, which I know I talked about, not great. We also looked at gas boilers. If you rely on electric resistance as your source of emergency heat for a building, it's going to drive up the size of your generator to prevent freeze damage. And the cost increase in the size of the generator really did not make a lot of sense. So we actually ended up justifying using the gas boilers as our backup. They only run, say, 200 hours a year. They're there in the event of a loss of power in the middle of the winter as well. And the net emissions difference between them was negligible. But the cost savings for the project were substantial, and were able to help justify something like on the previous slide, for example, adding PV as a screen wall. Sometimes, PV that's got some structure behind it doesn't always pay back that quickly, but we're able to do some creative things with the budget like that by focusing our effort. Next. So this one, for those of you, this design community is, one of the more experienced in the country at things like Living Building Challenge. This one is, pursuing a Living Building Challenge full certification, which requires not only net zero energy, but also no use of fossil fuel. And so here, thinking about this in terms of not only electrification, but also resilience, there's extensive on-site PV, but also battery storage for emergency. And more passive design to just start eliminating some of the loads altogether. So using trickle vents and fan-assisted natural ventilation helps eliminate some of our cooling and heating ventilation loads. Using geothermal heat pumps because they're a more efficient form of heat pump, that water-to-water heat pump, for example. Exhaust heat recovery, high performance envelope, things like that, that enable the building to withstand some of those more extremes in temperature and do it in an all electric and affordable way. And so you see here, this site, is trying to leverage, a lot of roof area that has PV, and we actually use that as our budget for what the loads in the building could be to do it all on site. Next. This project is a middle school out in Ashland. For those of you that work on K through 12 facilities, know, if you're not attempting to make them net zero or net zero ready, you're probably not doing it right. And the opportunity here was clear, with the land availability, say for ground source heat pumps. We looked at ground source heat pumps, we looked at VRF, we looked at traditional forms of chilled water, water cooled and air cooled. And I believe we're going with the geothermal option because of the land availability. So it makes our building really efficient, it makes it resilient to those extreme cold winters, but also enables, as schools, especially in Massachusetts, are using air conditioning. That's actually a good thing when you have a geothermal system, because you need to reject heat to the ground from the summer from your air conditioning to use it in the winter. Next. So this one, this is a large government office, and it's all three buildings, but the first building on the upper left was designed not that long ago, about 5 years ago, major renovation. But the two buildings in the lower right that are in design now, the world has changed pretty dramatically in those 5 years. And these are big buildings. In total, the two buildings, about 1.4 million square feet. They're located in Washington, D.C. And so Washington, D.C., remember those renewable portfolio standards that Chuck talked about in New England, moving towards 80% renewable energy on the grid by, say, 2040. Washington, D.C. is going for 100% renewable energy by 2032, relatively early in the life of the system in the buildings. So we think about emissions over time, not just year one. So this is a plot of those emissions based on today's emissions rates, where they'll be in 2032, and through the life of the system. The top line is the LEED baseline, which is a modest, efficient building. And we looked at a couple of options. The one on the bottom, that purple line, ultimately is that electrified solution. The green area is our carbon emissions savings over the life of the system, over through 2055. And that equated to, I think it was about 43,000 metric tons of CO2. And I'm an engineer. I love numbers. I don't know what the heck 43,000 metric tons of CO2 is, what that means. So we try to quantify this, and I recommend for those of you, working with your clients, come up with a way to translate this so that you get buy-in from your clients. The way we did on this project was actually the amount of carbon, the annual average carbon emission savings over the life of that system is the same amount of carbon that a forest the size of the two largest parks in Washington, D.C. could sequester in a year. Now, these parks are so large, and I actually, I'm newer to the Boston design community. I was in Washington, D.C. for about a decade before coming up to Boston. And back when I was younger and I was training for marathons, I'd dive into these parks and do full marathon training, and I'd never leave them. They're so large. So it's such just a grand scale that the impact that we could have by electrifying our buildings could be. Next. For those of you working on passive house projects, especially those that are actually pursuing a passive house certification, they strongly encourage you to go all electric, and by leveraging that high performance, super high performance envelope, it makes your building more resilient to swings in the climate, but also enables it to be net zero. This building at Williams actually was on a unique part of the campus where it didn't really make that much sense to extend the campus utilities to it. So by being its own little island, going all electric made all the more sense. Next. And at the other end of our kind of campus perspectives, those of you, I'm sure, work on a lot of different campuses, and they're all trying to grapple with these commitments that they've made towards being carbon neutral. This is Colby College. Colby College actually, those of you that were on the presentation a month ago or 2 months ago about campus decarbonization are already familiar with this, but they were looking for strategies to decarbonize, and some of those that we looked at were, expanding their biomass plant, but also leveraging a borehole thermal energy system, basically a geothermal system, distributed heat pumps, air source heat pumps around the campus. And we looked at it centralized versus decentralized, all with the goal of shifting away from that steam, which requires burning something and putting CO2 into the atmosphere, and moving the campus towards hot water to give them the opportunity to leverage the technologies that are available today and also into the future to heat their building in a carbon-free way. So with that, how do you decide on electrification? Now, I'm sure this group, you're like, we're electrifying anyway. Why are we even asking this question? But we've got to bring our owners along with us. And so we think about this in terms of a spectrum of electrification. On the lower resilient end of the spectrum is not doing any electrification at all. And frankly, I'm sure you've worked with a lot of owners who they're just not interested. They, for whatever reason, because of energy costs, because of familiarity, because of whatever it is, they're just not interested in electrifying. But as we move along this spectrum, you can design for future electrification, and I recommend that it is our responsibility as design professionals to at least enable the building to become an all-electric building. And actually, for those of you working in the city of Boston, the BPDA is now requiring you to have a plan for your building. If it's not all electric now, how will they electrify it in the future? Further along the spectrum to the right is partial electrification. This is important because, that Cape Cod example, for example, or those of you working on hotels or res halls or high-rise apartment buildings, if you can electrify, say, your building heating loads, but you maybe don't get to, for whatever reason, electrify your domestic hot water loads, you're still doing a good thing. So electrifying part of the loads now, and then enabling that future electrification of the last bit of the road. Then you go full electrification, just go for it, which really, I think, should be the goal that we go for. And not only just electrification, but thinking about electrification plus storage. So as Massachusetts starts to develop a grid that starts to reflect, say, Texas or California, and we need to ride out that time of use, the emissions at different parts of the day, having that storage or the capability for storage in the future will help our buildings kind of adapt to the emissions in the grid at any given time, and reduce the emissions overall from the building through scope 2. And with that, with 8 minutes to go, we're going to close on some recommendations and open it up for questions. So you got to discuss this at the very, 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 very beginning of the project with your owner, with your engineer, and consider how long the owner is going to own and operate the building, because they could be subject to things like, we all know BERDO is going to, in the city of Boston, going to impose emissions limits on existing buildings. We also know, owners, especially institutions, are thinking about their long-term emissions. Are they going to be subject to any kind of penalties? How can you get out in front of that? investigate whether sufficient space exists for heat pumps, and if not now, plan for it in the future. I know space is always a premium, but you've got to have a plan to electrify right from the beginning of the project, regardless of whether you're actually going to use that space, because we know the life of our buildings, they're going to electrify. Coordinate with your electric utility earlier than you typically do for things like electrification, but also electric vehicle charging, because the earlier you do it, the more heads up you give the utility to be able to extend service or upgrade service in the area of your project to support these loads. And we know there's going to be a transformation of the grid and the distribution. We want to make sure that your buildings are able to tap into that and collaborate with the utilities. And last, if you can't convince your owner to go for full electric, work on them for partial electrification, and at a minimum, design for future electrification, or at least allow space for it. So with that, thank you. Here's Chuck's and my contact information should any of you have any questions or want to follow up with us directly. But here are these last 6 minutes of the evening. I will open us up for questions. You're welcome to either put them in the chat or come off of mute and ask your questions. Thanks.
So do you have any tricks or trade ideas for us to help us convince our owners of electrification? I think that's the thing where we understand the positives of it and that we're all going to be going towards that, but that extra dollar sign for operation costs is hard.
Yeah, fair. So I do look at it through carrots and sticks. So New York City projects, very soon Boston projects that are going to be subject to carbon pricing in the future, and it probably will be in many more places in the life of the building, is a stick, a way of convincing them to make that shift earlier. Leaning on if they've made any kind of institutional commitments, that's one way of doing it. And quite frankly, one of those examples, and I'm not going to tell you which one, the client, we had the meeting at the very beginning, introduced electrification. They said, that's really interesting, but no thanks. And the design team has steadily pushed the entire project to electrify more and more and more. And we got there, but it requires constant pressure. And I'd also ask, and I'm saying this as an engineer, but this is something you as architects can also work with your engineers, or you as sustainability consultants can push your engineers on, is, at the beginning of the project, when you introduce a bunch of different options for systems, why aren't most of them or all of them electrified? Or, you may have to, out of just due diligence, acknowledge, fossil fuel-based heating systems, but at least, start defaulting into, we're going to electrify unless the owner is not comfortable with that. We just have to kind of shift like what that baseline or what that default is. And we'll get there as an industry. Now, there are lots of developers or more cost-driven types of owners that they're just not there yet. And that's where that planning for future electrification comes in. And that may mean, and I say this again as an engineer to a large group of architects, but it's virtual, so you can't actually throw things at me. Give your electrical engineer some room, a little bit, thanks, so that they can allow the building to electrify in the future, come up with that plan, because the building may change owners. It may be subject to future requirements, but make it so that when you, as the design professional in 20 years who are responsible for renovating that building, give them a way to do it. Make it easier on your future friends. So another question came in the chat. Have we looked at DC electric site grids? I assume he's talking about microgrids. Yes, and so some projects, we didn't show them here, we do have the opportunity for microgrids. One interesting thing, when we work at college campuses, even the ones that provide us with steam, and I kind of implied steam's not good, it's based on fossil fuels, but when you have steam generated as part of a cogeneration plant In fact, using that steam actually makes the central plant more efficient. Otherwise, it's just emitting to produce electricity, and you're not taking advantage of all that waste heat. So whether you're using kind of a campus electric grid or more like smaller microgrid, you have to kind of look at those opportunities. And so I know a lot of the architects here I've worked with, a lot of you do kind of master plans or work with developers on multiple buildings at a time, or work with institutions or universities. And so these are the types of the conversations to have, like expand the scope of your project to think about, well, how does your project act as an opportunity to partner with the building next door, or the building across the street, to help kind of everybody move in this direction.
Yeah, and Patrick, just to build on that, we have projects as well that will use something like a CHP on a microgrid, maybe for the next 10 or 15 years, and that is using fossil fuels. It is using them in a very efficient way, but that might run for the next 10 or 15 years. That gets a ton of savings for what would have been maybe a much less efficient, way of generating heat before, and allows the enabling of a future more electrified system, whether it's fuel cells, ground source, et cetera, to, for the long term. So definitely, don't rule out combined heat and power just yet. It could actually be a good way to get some of that future electrification that Patrick touched upon.
And so with that, with seconds to spare, thank you. It's been an honor being a co-chair for the Boston Society of Architects Committee on the Environment. I put the link in the chat for maybe the last time for you to get some continuing education credits. But again, congratulations to Laura and Beth, our new co-chairs. We look forward to the year of programming that you're going to bring us. I'm excited to continue on with the committee with you all. Thank you all for coming tonight and for your participation in the election, BSA Committee on the Environment first. And good night. And next time we get together, it'll be part of Laura and Beth's tenure. So thank you.